Superconductivity, complete disappearance of electrical resistance in various solids when they are cooled below a different characteristic temperature. This transition temperature varies for every solid, but it is generally below -253 degrees. When resistance falls to zero, a current can circulate inside a material without any dissipation of energy. This causes an increase in conductivity.
Traditional aircraft rely on fossil fuels, which contributes significantly to the greenhouse gas emissions, which is about 2 to 3% of global CO2 emissions, totaling approximately 950 million tonnes annually. If current trend continues, from aviation we could see a triple by 2050, which is about 2.7 billion tonnes annually. Superconductors aid in enhancing aircraft efficiency by reducing energy consumption and weight, leading to more sustainable electric or hybrid aircraft. This technology has the potential to significantly cut future aviation emissions.
One of the most exciting aspects is the development of high-temperature superconductors. Unlike earlier superconductors that required extremely low temperatures, these newer materials work at more manageable temperatures. This makes them more practical for the real-world applications, such as the integration of superconductors in the Airbus Ascend program. This is the perfect example of how technology can address global challenges by reducing carbon footprint of aircraft. We are making a positive impact.
One of the most cutting-edge developments in the sustainable aviation industry is the Airbus Ascend program. Ascend, which stands for Advanced Superconducting Cryogenic Experimental Powertrain Demonstrator. Airbus is using superconductivity to push the boundaries of what's possible in electric and hybrid propulsion, where electric planes are not just for short hops, but can power large aircraft over long distances.
First off, low power densities. Airbus is working on making this system 2 to 3 times lighter than conventional aircraft systems. By using superconducting materials that practically eliminate electrical resistance, this makes them 97% efficient in the powertrain, with 30 kilowatt per gram in power electronics, thanks to superconductivity.
The superconducting powertrain they're developing can scale from a few hundred kilowatts to a multi-mega output. To put that in perspective, getting an electric aircraft the size of city-hopping turboprop off the ground requires 8 megawatts of power, and Airbus is well on its way to making that a reality. Superconductivity only works at extremely low temperatures, and Airbus has nailed that by operating their systems with liquid hydrogen at -253 degrees Celsius with liquid nitrogen at -200 degrees Celsius.
Airbus plans to integrate these technologies into a demonstrator by 2025, moving one step closer to their goal of flying a hydrogen-powered, zero-emission aircraft by 2035. This is happening, and it's setting the stage for future of aviation.
Here we have a setup that includes a superconducting material, which is cooled using liquid hydrogen and a small magnet. When we cool the superconductor below its critical temperature, it enters a state where it has zero electrical resistance. But what's even more amazing is the Messier effect. Liquid hydrogen is incredibly cold, and when it comes into contact with our superconducting material, it cools it down to a point where it becomes superconductive.
Watch what happens when the superconducting material is placed on magnets. Pretty amazing, right? The superconducting material levitates. This happens because as the material becomes more superconductive, it expels the magnetic fields from its interior. This phenomenon is known as the Messier effect. The expelled magnetic field creates a repulsive force, causing the superconductor to float. Not only does the superconductor levitate, but it can also move smoothly along the track as if it's gliding on air. This is due to the frictionless movement enabled by the interaction between the superconducting material and the magnetic field.
Liquid hydrogen is not just a cooling agent, but it is also being explored as a clean fuel alternative for aircrafts. Combining superconductivity with liquid hydrogen could pave the way for the revolutionary advancements in how we power and designed for future aircraft, just like how Airbus is aiming to do. Superconductive magnets used in aircraft propulsion systems can be up to 100 times more powerful per unit of weight compared to conventional electromagnets.
A superconducting electric propulsion system uses superconductors to transmit electrical power with zero resistance. This enables highly efficient and lightweight motors for aircraft, reducing energy losses and improving overall fuel efficiency by up to 20% compared to conventional systems when integrated with SAF.
All aviation fuel, which is known as the SAF, is a cleaner alternative to traditional jet fuel, which is made from renewable sources such as plant oils, waste materials and other biomasses. SAF can significantly reduce the greenhouse gas emissions by 80% from aviation, helping to make air travel more sustainable.
Efficient superconducting systems can reduce the demand of SAF engines. For instance, superconducting systems can reduce electrical energy usage for SAF engines by 10 to 15%. This directly benefits SAF engines by allowing for higher fuel utilizations and lower emissions.
Yes, superconducting technologies enable the development of advanced propulsion systems. For example, superconducting motors can improve the performance of electric or hybrid aircraft. In such systems, SAF or solar panels can be used more efficiently, enhancing the overall environmental benefits.
So, do superconducting technologies aid the decarbonisation of pioneering aircrafts?
Yes, through several factors.
High temperature superconductors work at more practical temperatures useful for aviation. Airbus ACEN, developing superconducting tech for long-distance electric and hybrid aircrafts. Lighter systems. Superconducting propulsion is 2 to 3 times lighter and 97% efficient.
Superconductivity eliminates electrical resistance, boosting conductivity at low temperatures. Aviation emissions. Aircraft contribute 2 to 3% to global CO2 emissions, potentially tripling by 2050. Efficiency boost. Superconductors reduce aircraft energy use and weight, aiding sustainability.
Cryogenic cooling uses liquid hydrogen and nitrogen for high power at ultra low temperatures. Zero emission goals. Airbus targets zero emission aircraft by 2035. Magnetic levitation. Superconductors expel magnetic fields, enabling frictionless movement.
Hydrogen as fuel. Liquid hydrogen cools and fuels advanced aircraft designs. SAF efficiency. Superconductors make sustainable aviation fuel, which is SAF, more efficient. Power magnets. Superconducting magnets are 100 times stronger per unit weight.